So, first of all, welcome to the course. I'm pleased that I am running this course once again. And if participants are there, I shall start by, first of all, I'm going to just to introduce you to the course. And the first slide is this one. These are the reference for this course. I'm going to use the Handbook of Slope Stabilization. It's a book that we published long ago. It's a little bit, of course, out of date because it's 20 years old. And also, I'm going to use my other book on soil mechanics in the light of critical state theories. The course is divided into 5 lectures. So I hope you are, please let me know if you are seeing my screen, the course program. So today we're going to cover this introduction, landslide classification and geological factors. The second lecture, which is going to be announced later on, we are going to cover risk assessment, debris flow, site investigation, soil slope stability, rock slope stability, rock slope stabilization, drainage, erosion protection is going to be covered by the third lecture. The fourth lecture is about walls, either gravity, concrete, soil reinforced walls, anchor, bolts, and nails. The fifth lecture is going to cover tieback walls, soil nailing, instrumentation, and alarm system. So I hope we're going to enjoy. The idea of the course is not to teach you how all the details of the design. The idea of the course is to transmit experience that we have gained over many years. So let's go to the second. Let me share the screen again. Where's that? Landslide classification. So that's the purpose of this lecture. I hope you can see my screen. So that's the idea. We're going to talk about landslide classification right now. The idea is to talk for about 1 hour. We're going to have a 5 minutes break or 3 minutes break, and then we continue. The whole lecture may last 1 hour, 20 minutes or so, okay? So workflow. So in order to analyze any slope, first of all, we have to do a site visit, and you can do mass movement classification, geology, topography, and site investigation. These are the data that you need to come up with a solution for any slope. Then we have site investigation will take into account geophysics, borehole and sampling, laboratory tests. So this is what we're going to do next. And we are going to talk about site investigation a little bit, not too much geophysics, because these would require much more knowledge than I have on geophysics, but I'm going to talk a little bit about that. And then we carry out stability and risk analysis. So the workflow, either for soil and rock, we are going to do drainage surface protection. We are going to analyze anchors and bolts and barriers. Today, we tend to use a lot of flexible, steel flexible barriers, which we are going to address at the proper time. And then we have lots of solution for this slope, like cutback retaining walls, soil reinforcement walls, tied back walls, and soil nailing. These are the main solutions in order to stabilize the slope. And then once we come up with a design, we have to think about instrumentation and alarm system, which is going to be addressed in our last lecture, the 5th lecture, okay? Landslip types. We are going to talk This is in the book, Landslide types after Pruden, Varnes, 1996. So we have fall, topple, slide, spread flow, and spread and flow. Let me point to here. Material type, we have rock fall, rock topple, rock slide, rock spread, rock flow, and we're going to talk about that. If they are soils, so if they are predominantly coarse, it's debris fall, debris topple, debris slide, debris spread, debris flow. If it's fine materials, we're going to have earth fall, topple, slide, spread, and flow. So these are failure types in soils. Circular failure, plane failure, creep, which we're going to have some examples to talk about that, flow, shallow failures, and plane failures, okay? But, and this is, I managed to get this kind of animation, which is available from the US Geological Survey, very interesting. And a circular failure, we can define the crown, where we have the main cracks, and the toe, in which we have the bulge of the material at the toe. And this is the slip surface that has been defined as a circular one, okay? These are examples. For instance, this was a case in Brazil that I have visited many years ago, and it's very clear that is a rotational slides. We have lots of photographs to talk about this. This, I have seen all these failures taking place in sedimentary soils from the central Brazil. During the construction of the underground, this should have been 92 to 94. They cut this for the railway lines, and they had this failure take place. And these are very interesting rotational slides, which I have found on the internet, and it shows how bad it could be, okay? Just cutting an existing road, okay? Rock slopes, we can have a plane failure like that, in which we have a plane slip surface. We can have a wedge when we have two families of joints intersecting. This leads to a wedge failure. And we have rock fall. We're going to talk about that. And also, sometimes in residual soils, we have sometimes a lot of loose blocks, either on rock or soils. And sometimes they have to be fixed, or some other measure has to be taken place. And this is a case of planar failure, very interesting animation from the USGS. And this is a case which I have been involved in stabilizing this kind of failure that took place. Rock fall is when we have very quick, the velocity of the displacement sometimes is very quick, and we have a situation like that. This can take place in residual soil. I've seen this occurring too many times. This is a carretera Sul-Americana in Ecuador. I have seen many rock falls taking place in this road. And this is one of the cases that I also found on the internet, and a very scary one. So if we geotechnical engineers do not do our job properly, that's what may take place. And also topple, when we have kind of a failure in which the slip failure is more or less vertical, and we have a fall like this taking place. These are an example of topping failure from Portugal. One of the roads in Portugal I have visited many years ago. Also, these are kind of topping failure taking place in Carretera Sul-Americana in Ecuador. I visited this site. It was 2001, I think, when we gave this kind of course in Ecuador as well. Wedge failure in Carretera Sul-Americana. Ecuador as well. It's kind of wedge failure. Okay. And plane slides. This took place in Santa Cruz Fortress. It's a fortress in Rio de Janeiro, built by the Portuguese in 18 something. No, it was built well before that. It was built by the time the city was founded in 1567. Soon after they built this fortress to protect the entrance of the bay. And in 2020, so 4 years ago, this failure took place. This is a place I used to cycle, so a very dangerous one. I'm happy that at this time I wasn't there. Okay, but that was a big plane slide in which a big wedge slided. Debris flow are very common when we have lots of rain on the mountains, and this leads to rapidly moving mix of water, mud, trees, and other material that flows down valley and can travel great distances. An example of that is a mud flow taking place in a motorway not far from Rio de Janeiro, Brazil. I've seen this so many times. And translational slides, this on the right-hand side took place very close to my home. It was 1988 and destroyed the house of a friend of mine, not far from my home. These are translational slides with little rotation along a flat plane parallel to the surface. Okay, this is a very interesting one. This seems to have taken place in Slovenia. It's a mine, and it was a blast-triggered slide. I got also from the internet, but it's so interesting. They decided to carry out blasting at the top of the slope, and let's see what happened. Wow. It's a big landslide that took place, triggered by blasting. Okay. Scary. Destroyed the mine. And this is a landslip triggered by earthquake. This took place in September 2023. And it was a hotel in Morocco. I visited the site. Morocco, I visited the site, and I carried out a preliminary design to stabilize the slope. And what was very bad, I visited also the hotel. It's a beautiful resort with lots of swimming pools, etc., etc. The hotel was nearly destroyed, and so they might abandon the site. That was what we heard when I visited the site in January this year, and I carried out a design for this to stabilize this slope, which I'm going to talk with more detail when we at the soil nailing class. Okay, some shallow slides I've seen taking place. Shallow slides. This is another one. I have done some work, and in 2000 I was involved in this many slides that took place in Campo do Jordão. It's a town in São Paulo, Brazil, and they had lots of rain, and they invited me to work with them on some stabilization work that we did later on. But they had major slides triggered by very severe rainfall. This Andes, Ecuador as well, La Carretera Sul-Americana, one of the largest landslides I have seen. The height, you can imagine the height of this is over 100 meters. As you see a car here, very small car. So it's a big challenge to stabilize this slide. Another photograph. And Andes, Peru. In Peru, there are places where they have very little rain. Sometimes there's a desert. And this is the case. While in Ecuador, they have lots of rainfall. Peru, they don't. So I have been working in Peru on mining some of the mines, and they have nearly a desert, and they have this kind of landslide taking place far away, so no one is even thinking of stabilizing it. But very interesting situation that takes place in some of the sites I have visited in Peru. And this is also a town in Brazil, which Morro da Forca, this stands for Scaffold Hill. So it's where the Portuguese, during the Portuguese, when Brazil was a colony of Portugal, this is where the scaffold used to be, and they used to hang people here. And there was a major landslide after a lot of rainfall that took place. It's a very interesting town. It's a small town, and everything is left as it was in the 17th century when it was built, and all the houses, all the architecture is based on that kind of architecture. And this took place in 2022, so 2 years ago, destroyed one of that beautiful house over there, as you see. This took place after severe rainfall in this town, Ouro Preto, which stands for black gold. Okay. Scary. This is something that took place in 2023. A lot of the state of São Paulo, close to the sea. So they have lots of landslides taking place, and so this is one of the problems that we face when we have lots of rainfall. Okay, look at that, nearly destroyed lots of houses, etc. That's good. Anyway, flow. If the flow is slow, we can call it creep, as I'm going to talk about later on. It's a continuous movement. Sometimes it has an undefined slip surface, and it has a drained behavior, okay? And so, can take place on gentle slopes, as I'm going to show you, okay? And fast if we have mud flow or debris flow. So these are the type. And fast mud flow, debris flow takes place on very steep slopes, and it's a viscous fluid, and the behavior is undrained. Okay. Rapid flows, earth flows, structural collapse of medium dense soils. Sometimes it takes place on sandy and silty soils. Pore pressure increase. And mud flows, usually very rapid flows on sensitive soils, debris flows, and debris flows can be an avalanche or rock blocks, soils, and debris, okay? So these are debris flows that usually take place on mountains when we have lots of rain. I've shown you some cases, and this is the animation by USGS, which is very interesting. Some examples of debris flow in one of the roads I have been to many years ago, 1990, debris flow. This was the largest, one of the largest debris flow I've ever heard about 200,000 cubic meters of soil displaced. It was huge. As you see here, these are a big viaduct, and you have an idea of the size of this large debris flow due to very intense rainfall. So, landslide classification according to soil disturbance. Virgin landslides, they occur in a disturbed soil with mobilized peak soil strength, okay? Or reactivated slide, old slides occur in undisturbed soils at a previously occurring landslip surface with mobilized residual soil shear strength. So this is the classification: virgin landslides or reactivated landslides. Anthropic triggers: removal of vegetation, what we sometimes spill from water or sewage pipes, incorrect cuts, sometimes too steep, very loose fills, not properly compacted, and waste deposits incorrectly placed. So these are the main anthropic triggers for landslides. And landslip triggers, according to this classification from Guidicini and Niebla in 1984, these are the agents pre-existing: geology, morphology, climate, gravity, temperature, vegetation. Triggering mechanisms: rainfall, erosion, freezing, thawing, temperature, changes, solubility, groundwater change, animal and anthropic activity. And triggers can be rainfall, snow thawing, erosion, earthquakes, waves, wind, anthropic action. And the causes: internal causes: temperature change, shear strength, decrease due to weathering; external: geometry change, vibrations, as I have shown you; and intermediate: groundwater level rise, suction, reduction, water filling joints, and rapid draw and pipe. Okay. And these are landslides trigger mechanisms adopted from Varnes, 1978. Action: load increase by removal of soil or rock mass; surcharge, seismic load, horizontal pressure; strength decrease, material characteristics, change of variable factors. And the phenomena associated with that: erosion, landslip cuts, weight of rainfall, ice, snow, natural deposition of soils, weight of vegetation, building of structural embankments, and seismic load: earthquake, waves, volcanoes, vibration, traffic, induced seismic loads. Horizontal pressure: water-filled joints, freezing, expansive soils. And material characteristics: geotechnical characteristics, stresses, and weathering, shear strength loss, and groundwater rise. So these are causes. Flows can be shallow, usually slip surface less than 5 meters depth, or deep when the slip failure is over 5 meters depth. And it can be progressive, slowly accelerating, as we have shown some of the videos I have shown you before. And post-failure, with mass still moves. Landslide velocity can be very high, average, low, or very low. Very high, we talk about meters per second, high, meters per hours, average, meters per day, low, centimeters per day, or very low, centimeters per year, as I'm going to show you some cases I have been visiting in the past. This is Tapesco slide. It's in Costa Rica. I visited the site in 2000. So it's a big slide limit. So we talk about this 500 meters. This should be over 500 meters in length, and width should be over 500 meters too. And there's a town with 10,000 people not far from the possibility on the path of these landslides. People were looking at this and trying to understand this. The photograph that we have taken, the landslide was starting from the top of this mountain. And this is a cross-section that we came up, residual soil, shales, and breccia. And this is the possible slip surface that was forming. And people were scared about the possibility of these landslides and the fact that this small town was in the path. Fortunately, it did not occur. Lateral spread. This when material extends, spreads on gentle slopes. This type of ground deformation often associated with earthquake shaking. So I'm going to show you a case which I visited long ago, which is Puriscal, Santiago de Puriscal in Costa Rica. Santiago de Puriscal is a town we say 10, 20,000 people, and a very gentle slope of about 5 degrees, that's more or less. And the whole city, the whole town is moving. And when we visit the site, sometimes we see on the ground some cracks taking place, etc., etc. And this was very, very scary. I visited this place in, I think, 2000, 2001, more or less. This is Santiago de Curiscal, Costa Rica, and when we walk along the town. This is the kind of crack that we see due to these movements. And this is the church, which has been closed because it's been because of the movements that led to cracks and damage the church. As you see here, this lady was the mayor of the town at the time, and you see some tilting of the building towards the right-hand side, and the building was totally closed, and this is inside the church. This is what we see due to this slow or very slow movement. And this is also Andes, Ecuador in 2000, and we visited many sites with problems with the Ministry of Public Works at the time. And this kind of creep that we visited was the amazing site when we see soil and surface material that slowly moves down a slope. And this is one of the biggest landslides I've ever seen. El Turi, Ecuador. This is more or less the site. There's a university here called Azulay University. This is Pan American Road in which we were traveling to see these landslips. And this is something like 4 kilometers by 3 kilometers. It's a major landslide. The whole area was moving. And this more or less the cross-section takes place. It's a very large, a very long slip surface. And this is where the buildings are, which of course are damaged by the movement. It's called, the geologists call it Azogues Formation. It's by sandstone and siltstones. And this, what I have seen, many houses, many damaged buildings. This is an attempt of one of the owners of this building to prop his house. Very interesting. Of course, totally ineffective in this kind of situation. And what we see as an indication of movement, all these poles are tilted, lots of water. This is the upper part of the slope. Evidence of movement. We see here these tilted poles, tilted trees, tilted pole here, evidence of movements, a slow movement. Now I'm going to talk a little bit about some slides I have seen in Rio and Hong Kong and how they compare. Okay, so I call this a slope tale of two cities. There is a chapter of the book which is devoted to talk a little bit about this experience. So as you see here, Hong Kong and Rio, they are, let's say, sisters in terms of sister cities, in terms of slopes, because it's a narrow piece of land and squeezed in between the sea and the mountains. So almost the same. And both do not have a lot of earthquakes. We don't, neither in Hong Kong nor in Rio, and a lot of rainfall. So the problem is rainfall. All these landslides that I'm going to talk about, they are triggered by rainfall in the end of the summer. Okay, so when we have a lot of rainfall, that's what happens. We have lots of landslides. And this was first really reported in 1580 by this gentleman here, was Priest Anchieta. He was a Jesuit that came to sent by Portugal to teach young children, etc., to to bring them to Catholic religion. And he was the first to report in 1580, Father Anchieta. And then, very interesting, in 1711, this French admiral, René de Guertois, he invaded Rio de Janeiro and to arrest the governor of Rio de Janeiro during the time of Portuguese rule. And he was very successful. He arrested the governor and sold him back to Portugal again. This took place in 1711. And the battle against the Portuguese was carried out under severe rainfall, according to the records that we still have. So this is the French either we can not sure we can call him pirate or admiral or whatever, but he was very successful. He entered the bay and then fought against the Portuguese. From 1906 to 1924, we have lots of records. For instance, this was the Central Rio flooded in 1924, this 1911, this 1906. Have found lots of reference about slope instability and floods. And then 1966 was the big Laranjeira slide. I was 17 years old, and this took place in Rio and killed. There was a big building here which was knocked down, and this big building, when it fell, killed about 200 people. And on the next day, the mayor of Rio decided to create, this was what happened, 140 millimeters in 24 hours rainfall, nearly 200 casualties. And on the next day, I still remember, the Geo Rio was found. It was Geo Rio, it is yet an organization to look after slopes in the city to avoid this kind of disaster. And it was founded in 1966. This organization does? Slope stability works, design review of foundation of slope stabilization, risk reduction program, risk mapping, and they run what we call the Rio Watch alarm system, which was developed in 1996, 97 I worked on this project. And this the alarm system that we're going to talk in the last lecture of this course, okay? So, for instance, in 1968, you probably have heard about Christ the Redeemer, and they found this loose block, big one here, and decided to stabilize it with bolts. It was some anchors as well, rock anchors, and these counterforts here to stabilize this loose block. Also, in Rio, I've seen this taking place in 1968. I was in School of Engineering at the time, and lots of work took place after that disaster. And this one of them, they put lots of drainage system to improve slope stability, like this drainage channel, to avoid water ingress into the soil, which is here, okay? These examples of tieback walls that have been built to this, not far from where I lived long ago. So lots of work, drainage work, cascades here, and ditches, etc., etc. And from 1967 to 1988, no severe rainfall, no severe accidents, people relaxed, and then disaster strike again. Now, this was Lagoa Landslide 1988. Lots of mud flows at the Kititi Mountain in 1996. This is one of the most important district of Rio. Lots of landslides took place here. No casualty, fortunately. And this was close to my home in 1996. Destroyed a friend's house somewhere here. And this is another one, landslides, which due to severe rainfall. And this is not far from where I lived, and this you see a rock scarp, and here drainage works taking place. But even though the rainfall was so severe that led to these accidents, Rocinha Hill, they put these channels late after this accident, and there was a loose slab, and they fixed this loose slab. This was the highest scaffold I've ever seen, 150-meter tall, just to put this to fix this loose slab. This took place, and also in what we have to take a lot of care is the portal of tunnels, in which if we have a landslide, it disrupts the traffic in the sea. This took place in 2007. Okay, this kind of landslip. Later on, lots of work have been done on both parts of the tunnel. This is the main tunnel. Let's have a look at Hong Kong as well. I was there between 96 and 97 and 98, and I worked as a visiting professor at the City University of Hong Kong. And Hong Kong is a very interesting experience for me. This happens to be my name in Chinese when I worked there. I'm very proud of having a Chinese name. And this is Kowloon, the continent, and this Hong Kong Island, and a very mountainy region with not enough space left to put the buildings, and lots of accidents took place along many years. And this is the old airport, which I now they have a much better airport at Lantau Island, somewhere here. But this is how it was in 1996. And in 1977, well, before I visited Hong Kong, they had more or less the same situation, in which they had the Po Shan landslide in Hong Kong Island. And this landslide also knocked down a building, and lots of people lost their lives. And they created a similar system to the GeoRio, which is the GEO, Geotechnical Engineering Office. This is the Kowloon Peninsula seen from the Hong Kong Island. Some of the landslides I've seen: Castle Peak Road, 97, Ching Choing Road, all these in Hong Kong Island. Kennedy Road, 1992. This was before I was there. And I learned from them in 1996, they had the Hong Kong alarm system, in which they have lots of rain gauges, all about 30 rain gauges in the whole network, in which they were all automatic and could measure the rainfall and issue alarms. And this is what we learned from them. And I happened to be the one who brought the same idea to Rio. And then I organized a visit from Rio de Janeiro officials, engineers. They went to Hong Kong, saw the system working, and we replicated in Rio later on, which turns out to be the Rio Watch Alarm System, which I'm going to talk about in our last lecture. So what we learned about the GEO in Hong Kong, they decided, when they decided to put that, the difficulty is to have alarm level. And what they have done about that. With time, the meteorologists who analyze the data, the rainfall, etc., they come to a trigger level in which they have to decide whether or not to issue an alarm. And this is a difficult situation in the beginning. If you don't have experience before, how can you issue an alarm? And then if you do issue an alarm and nothing happens, the system loses credibility. So in order to have a credible system, you must have experience and meteorologists looking at that much more than geotechnical engineers. And I remember later on I helped to design. I did some consulting in Malaysia for them to install a similar system. And one of the questions I remember they asked me, when should we start issuing alarms? I said the best situation would be to wait for a few months and learn, to have meteorologists learning from the experience, etc., and then after some time you issue the alarm. Well, I'm talking about the technology which was available in 1996. Now it's much better. We have a much better way of predicting bad weather, and there are numerical analysis, etc., which everything that we have today. This was not available at that time. Okay, and this is Hong Kong experience in which the accidents that take place after they issue the alarm, and this was reduced a lot. The accidents after by having this alarm system in Hong Kong, and that's why we replicated that in Rio much longer ago. This retrofitting of slopes, this also what Hong Kong does of their slopes. I have visited a few sites in which they were retrofitting slopes before and after retrofitting. That's pictures before and after. I visited some slopes like that. And they have what they call the risk reduction program and foundation stabilization design review, inspection, slope inspections. This is very important. Risk mapping, stabilization works, and quarter clearance. I visited one of the last quarters they had in Hong Kong. They had a lot in the 70s, but when I lived in Hong Kong, much less. And they have the alarm system, which is seems to be very effective. And then that's it. So let's do a quick break, and then we go to the next discussion. Quick break, only 2-3 minutes, okay? And I'll be back soon, okay? Okay, let's go to the next step, which is going to be the geological factors. And if you have any question, please write the chat, and I'll be able to answer or to discuss anything that you might be interested. Okay. In the meantime, let me go back to share screen, new share. I hope you can see my screen now. Now we are going to talk about geological factors intervening in the slope, in the landslide. Okay, and what are the geological factors? We have different types of rocks: igneous magmatic rocks, sedimentary rocks, metamorphic rocks. We can have joints, which means non-rock. Joints are very important, and all the weather products, which are soils from weather from rocks. And these are an example of jointed hard igneous rock from Ancon, Peru. These igneous rock blocks, hard rock boulders and blocks separated by weathering. This from Minas Gerais in Brazil. Okay. These are sedimentary rock, cement and sandstone subhorizontal joints from Tarija in Bolivia. As you see here, cemented sandstones, and as you see the color, sandstone very always very red. Sedimentary rock, like we have here sandstone and siltstone, and very soft weathered shales from Tarija in Bolivia. Metamorphic rocks, these are weathered phyllites from Minas Gerais in Brazil. What's interesting, it's a layered kind of rock, and has peculiar landslip surface, which we can easily detect. And these is a weathering profile of gneiss. When you see here, we see the topsoil, we see saprolites, and we see jointed rock. Weathering products, structured soils. One of the main slides, main photographs I have of this is kind of weather products from gneiss, and we see here this lichen sites, and at the top, what we see here is a more mature soil. It doesn't have the characteristics of the rock, but the young residual soil, which is all this part at the bottom. Let me share the pointer. Yeah, all this part here is very structured soil, so it has preferences in terms of landslip failure, which should be inclined like that. And this doesn't have any more because these are more mature residual soil. Okay, so geological features are faults, joints, padding, schistosic plains, stress relief joints, tension cracks, sheared plains, and weak layers. Okay. Jointed rocks. These are in the example of Cerro Verde mine in Peru, where we did some work in the past. Weathered layers in jointed rock, jointed gneiss, as you see here, jointed gneiss from Brazil. This slide along relief joint, this is have shown you before. This photograph, it's as you see here, a relief joint, and landslip took place, a planar rock failure. These are overhanging slope, cement and sandstone from Bolivia, very interesting one. And these are slip surface. If you have a homogeneous material, So the trend is to have a simple slip surface. However, if you have horizontal layered soil, this is the kind of slip surface you may have. So the joints are going to influence the geometry of the slip surface, as we see here. If we have a dip, which the inclination of the joints greater than the inclination of the slope, this is the kind of slope that may form, okay? So if the dip is less than slope, this is a different situation that may form. And we have what we call, the geologists call the daylight feature, in which the joints are going to appear on the surface of the slope, okay? Inclined layered soil. And these are complex cases in which we may have, for instance, in this case, dikes. This is very common in gneiss geology, in which we have migmatite dikes in intrusion rocks in gneiss formation. Okay, you have a kind of complex joints here. And I'm going to talk a little bit about this Soberbo slide. Soberbo slide was a slide that took place in 1967 in Rio de Janeiro, Brazil, and took years for people to understand what really happened. It was, for me, one of the most difficult slides in which the interpretation of what happened took many, many years. And this took place in 1967. It's it's a mountain, and we have this this road here at the top, which also be a road, and this is the funnel road at the bottom. And there was a lot of landslide. The landslide was moving slowly. It was not moving very fast, something like a few centimeters per week or per month. Okay, but this took place and took a lot of effort from Georio, the people of the Rio de Janeiro Slope Authority, to understand what happened. And they did a lot of work there. They put instrumentation, and they have instrumented station. They measured displacement. They had inclinometers. And the inclinometers, I remember, with time, they would be sheared, the inclinometers. And this is a cross-section, okay? And this, what happened in the upper road here, the Soberbo road, the other road is down there, and it's a colluvium on jointed rock, okay? And they put inclinometers to understand what was going on, and these were sheared with the movements, and it took years for people to understand. There were 3 or 4 theses at my university, the university I used to teach long ago, Federal University of Rio, and people were concerned about rising of pore pressure, shocks, etc., until a friend of mine, a very good geologist, went to the site, and this was an aerial photograph of the time, of this Soberbo slope, and he noticed that there was a change in inclination, more or less at this point, another change of inclination, and decided to carry out inclined boreholes. Until then, there was a few boreholes, but they were all vertical. And then they decided to carry out some inclined borehole to study this. And what he found was a diabase dike. As a matter of fact, a family of diabase dikes. They were absolutely unweathered, okay, and a very weathered mass. So what happened was that it was like a dam. The pore pressure, the jointed rock here was that had a very high permeability, and when it came to this point, the water pressure would rise when it rained, and this was the cause of the movement. And he described then at least 2 diabase dikes along the path of this embankment, and this was object of additional work at this Soberbo road, and this is explained in the book that you may have access. Okay, so that's it. It looks like I finished a little bit earlier than I thought. And if there is any question and discussion, I'll be very pleased to share some ideas with you. Okay. Thank you very much. Let me check here. Okay. Thank you.